Hello, this is a presentation on the Drone Detection System project developed by the General Dynamics Land Systems portion of the Wireless Communications Enterprise, developed by Nevaeh Mellon, Eli Bostelar, Alexis Lang, Weston Mulker, Alex Caldwell, Ryan McKendry, and Cole Ruud. This is an overview of the sections that will be gone over in this presentation. Starting with a rough overview of the project itself, the reason this project was developed is due to the new security threats that are being posed by drones and new countermeasures that need to be taken in accordance with this. The goal of this project was to use a beamforming array in conjunction with a pan-tilt zoom camera in an attempt to develop a machine that can track the location of a drone in real time using a beamforming array, picking up on the frequency of a drone, and coordinating this to a camera, giving it inputs with coordinates to track the location of the camera in real time. This is also done with the assistance of a GPS system to consistently keep track of where the drone is, so as to make sure that our results are accurate. This is a rough graphical presentation of what the systems working together looks like. We have a 16-channel microphone array that is working in conjunction with a Raspberry Pi to pick up on the frequency of the drone, which then transmits its coordinates to the pan-tilt zoom camera, and this camera can then be transmitted onto a live feed. To start with the beamforming theory of how this machine works, the 16 microphones are effectively able to beam out beams, and these results from the beams, as in what is reflected and at what point, are digitized into code that can be transmitted to the Raspberry Pi. A graphical representation in both 2D and 3D is shown here. This is then used to assist the camera in finding the location of the drone. As for the camera that was chosen, this is a decision matrix with 4 cameras present: the ArduCam 12 megapixel and 64 megapixel respectively, the KKB 4G LTE, and the Waveshare 360. Shown at the bottom is the total number of points each of these accrued, with a higher number of points meaning it's better for our purposes, with the ArduCam 64 megapixel coming out as a clear winner due to its low price, its reliability, its resolution, and ease of configuration with other softwares. As for the microphone array, this came down to a closer battle, but was ultimately chosen by the UMA 16 due to its higher number of microphones than the UMA 8, and its significantly lower price than the 2 other competing microphone arrays, the Star 48 AC Pro and the Clear One beamforming arrays. As for the software, this is a graphical representation of what it looks like to run the beamforming array in real time. This is a heat map showing the frequency that is picked up by each of the 16 microphones shown by these dots, and in real time this will shift depending on what has the most notable frequency in that range. This is then able to transmit through the Raspberry Pi with the goal of getting these azimuthal coordinates generated from this heat map to the camera to attempt to track the drone. As it already came in the Raspberry Pi, this came with a lot of difficulties due to the fact the Raspberry Pi is a much older model, and there had to be a lot of integration done with the beamforming array. However, what was developed first was a demo that utilized the 4 arrow keys on a keyboard with the ArduCam to move it around, and this laid the basis for what we later did to transmit this information to the beamforming array. As you can see here, the camera is moving little by little, given each key press. As to continuations, as I mentioned previously, the demo code was retooled to be used in conjunction with the beamforming array. So the coordinates taken from the beamforming array could then be transmitted to the camera instead of a simple key press. But the lack of Wi-Fi capabilities in this Raspberry Pi made getting this code up and running rather difficult. The integration continued with the beamformer that was used in the vicinity of the drone, so the drone could fly nearby it. The frequency of the drone was recorded, and we had tooled the beamforming array to specifically target frequencies in this range of the drone's whirring and other general noises. The camera was wired to produce video feed from this, and the system was tested. Following this was a lengthy section of drone repair, where there were several issues with the drone not flying correctly, the Ardu pilot system not functioning correctly, and the GPS model functioning incorrectly. The GPS was very unreliable for a long time. You were unable to get a consistent feed that would reliably tell the location of the drone, which eventually led us to building a new drone with entirely new parts while reusing the previous GPS system in conjunction with a new GPS system to effectively have a double check of the location at all times. As for the drone legality, this drone was registered through the FAA, and all necessary precautions were taken to make sure this drone was safe and legal to fly on campus and test. As for the results, we have a brand new functional drone with more reliable GPS technology, a beamforming array which can successfully detect the drone's audio signature, and an integrated point-tilt zoom camera that is capable of keeping up with the coordinates generated by the beamforming array. The next steps would be to develop a way of detecting this at further ranges and testing this outside in real-world conditions instead of in a closed environment like we had tested it in. Other than that, other components like the camera and the beamforming array could be improved on, as the ones we use were relatively low spec. Thank you.